Okay, welcome everyone to this SPDE seminar today. So today we have Hubert Lacoin from IMPA. So Hubert did his PhD in 2010 at Paris 7 and then spent a few years in Rome and again in Paris before he moved to Rio de Janeiro in 2014. We're very happy that you are here today and give a talk about the Continuum Directed Polymer with Lévy Noise.
So thank you very much, Carsten, for the presentation and for the invitation. It's a great pleasure to give a talk here. So I'm going to talk about directed polymers today. So before talking about the continuum model and problem of scaling limits, I will just give a very brief introduction to directed polymer in a random environment. So okay, it's a model that is supposed to account for the following physical situation. So we have a polymer that is a long one-dimensional molecule, which lives in a higher dimensional substrate, higher dimensional solution. In this solution, you have impurities. Some of these impurities will attract the polymer chain, some other will repel the polymer chain. And what you want to figure out is whether these impurities will change the polymer configuration on a large scale. And really, the directed polymer in a random environment model is an oversimplified picture for this. And the idea is to see if we can see something about a very simple disordered model. So so this is the model we are going to study. So to model our polymer, we'll model the polymer by the graph of a nearest neighbor random walk in ZD. Okay, so okay, here I gave the picture when D is equal to 1. So if you want to model the 3D situation, so you would have to take D equal to 2. And to model the environment in each of the sites that this graph might visit, we put a random variables and we draw these random variables in an IID fashion. And then to each possible path, we associate a weight, which is just the product over the visited sites of 1 plus beta eta. Okay, we are going to choose our parameter beta between 0 and 1. This kind of models the intensity of the disorder. And for this thing to be always positive, we are going to assume that eta is larger than -1, almost surely. Okay, and then the directed polymer will simply be the measure on this set of paths of length n that to each path give a probability which is proportional to this. Okay, so somehow it's more convenient to think of this measure as a measure on the set of infinite paths. So if we take P to be the distribution of the symmetric nearest neighbor random walk on ZD, we'll just say that our polymer measure is a measure which is absolutely continuous with respect to P, and its density will be proportional to this product of 1 plus beta eta that I talked about before. And we want this to be a probability, so you will have to renormalize by something which is what we call the partition function. And it's just the expectation of this with respect to the random walk. So if you have already seen a presentation about directed polymer, or if you worked in the subject, it's far more common to see this density written as the exponential of the sum of the beta etas. Well, somehow this presentation are equivalent. There is just a change of variables between this and this. Okay, and you also have to change beta in between. But somehow for the specific problem we are interested in today, this presentation is just much more convenient. Okay, and you will see why in a moment. Okay, so I will not talk much more about the discrete model, and I will talk about what what we want to do today, which is to introduce a continuum analog of this directed polymer. So we want to replace the simple random walk by a standard Brownian motion in RD. And we, okay, then the next step is not completely obvious. Here we have defined the density of the polymer measure with respect to the reference measure by this. So we will try to define a new measure on the set of continuous trajectory, which has some kind of density with respect to the Wiener measure, and which should be given by something that depends on an environment. And okay, we want to define this continuum model in a natural fashion. In particular, we want it to be the scaling limit of the discrete model, in the sense that if we rescale our walk diffusively, so by square root of, well, if you rescale time by n and the transversal direction by square root of n, and if you send beta to 0 with a specific rate, well, let's say an inverse power of n, we want to have that this discrete, the distribution of this rescaled random walk under this discrete polymer measure converges when n goes to infinity in distribution to my continuum polymer measure. Okay, and this is, well, this kind of result that we will be interested in today. Okay, so actually this program has been undertaken already by Hubert, Khanin and Quastel in the case where the disorder has a second moment, and I will talk about that later. And our joint work with Quentin focuses on the case where the disorder is heavy-tailed, so that our eta, let's say, well, the tail probability of the eta decays like q to the minus alpha for some alpha between 0 and 2. And here I've written this as a pure power, but if you want, you can put also a slowly varying correction. This wouldn't be a problem. Okay. Okay, when you have heavy tail disorder, the noise that will appear in the limit in our model will not be Gaussian white noise, because okay, the continuum model introduced by Hubert, Khanin and Quastel is based on an SPD with Gaussian white noise, and the fact that the noise is not Gaussian kind of changes the approach you have to take to solve the problem, or at least it changes the approach we took to solve the problem. Okay, so I think it's an SPD seminar, so I will have to justify my presence here by kind of introducing an equation. So let me explain why these directed polymers are related to SPDs by introducing the point-to-point partition function. So okay, the partition function, you may recall, it was the renormalizing factor I introduced in a previous slide, the expectation of this product of weight for the simple random walk. We define the point-to-point partition function to be this partition function, but restricted to trajectories that end up at a specific point after n steps. Okay, and I will call that Znx. Okay, and I will introduce the discrete time derivative of Znx by, okay, what it should be. Z bar, it will just be the space average of Z among its neighbors. And the discrete Laplacian of Z, it will just be, well, the average among the neighbor minus itself. Okay. And what I claim is that this discrete, well, this point-to-point partition function, it satisfies the following discrete SPD. So the time derivative is equal to the Laplacian plus beta eta times Z bar. Okay, so because I'm justifying my presence here by this equation, I might as well give a short proof of it. So, okay, how can you see it? When you would try to compute Zn plus 1, in your expectation, for all the paths you are taking the expectation over, they all have the same endpoint. So you have this factor 1 plus beta, eta, n plus 1 that appears everywhere. So you can take it away from the expectation. Then another thing you can do is to say, if you have to be at x at the final step, then at the step before you have to be at a neighbor of x, and you decompose over all the possibilities. Okay, and then because you are in ZD, okay, if you know that you are at y after n step, the probability that you end up at x, which is a neighbor, is simply 1 over 2d. So you can just delete this and replace it by 1 over 2d in front of the expectation, and you get exactly the equation we wanted. And in fact, to get exactly the equation, you have to subtract z and x on both sides. Okay, so basically, we want something a bit more than just the limit of this point-to-point partition function, but this might be a good starting point to get an intuition and to see the relation with a continuous stochastic heat equation. So if we want to have a scaling limit that preserves both this time derivative term and this Laplacian term, we have to rescale diffusively. And in the diffusive limit, well, we will get the continuous derivative and the continuous Laplacian here. Now, if we rescale beta to 0, this beta eta term here should, because the etas are IID random variables, this should converge to a noise term. And somehow in this limit, one can expect that having z or z bar shouldn't make much of a difference. So as a conclusion, at least formally, the scaling limit of this equation should be the stochastic heat equation with multiplicative white noise. Okay, and because you have n plus 1 here, it's quite clear that this multiplication, you have to consider it as Ito multiplication. Okay, because you're multiplying with the immediate future. Okay, and for our directed polymer problem, the initial condition you want to consider is the Dirac mass at 0. Okay, so now let's say, I said white noise, but let me be a bit more specific. So when the second moment of eta is finite, actually the right thing to consider is Gaussian white noise, because if you consider eta as a distribution, okay, so if you place on each side a Dirac mass with intensity eta and x, and you rescale things properly, you will converge to a Gaussian space-time white noise in some Sobolev space. When you have heavy tail environment, okay, so somehow you have the same type of convergence, but in the same manner than a random walk with finite second moment will converge to Brownian motion, and a random walk with heavier moment will converge to a Levy process. Here we will converge to an alpha stable white noise. Okay, so let me say something more about this alpha stable noise and introduce, well, okay, give a general definition for Levy noise. So maybe most of you might already know what Levy noise is, but okay, when I introduce this definition, I will introduce a cutoff that is also useful for what I want to do later. So, okay, I want to define what's a Levy noise with intensity lambda on R times RD. So, okay, I give myself a measure lambda on R plus, which is such that 1 is integrable at infinity and U square is integrable at 0. And I will first consider a Poisson point process on R times RD times R plus with intensity which is given by Lebesgue for the first 2 coordinates and lambda for the third one. And then I will say that basically that my Levy noise with intensity lambda is what I obtain if I sum for every point of the process a Dirac mass at xt and with an intensity which is given by the third coordinate of the point. Okay. The problem is that if I do that, I might end up with a measure which is everywhere locally infinite. So I will have to compensate for the drift while I do that. And one practical way to do that is first introduce a cutoff. So I will sum over all the points which have mass larger than A. I will subtract to my process Lebesgue measures times kappa A, where kappa A is basically what I need to recenter the contribution of all the jumps between A and 1. And this will give me a distribution which I will call my truncated Lévy noise. And when A goes to 0, if lambda satisfies this, this distribution converges to a limit, which I will call the Levy white noise with intensity lambda. Okay, and in the case where lambda is equal to exactly this corresponds to the alpha stable noise. Okay, so this definition is somehow restrictive. So for instance, you can have an additional Gaussian white noise part in a general Levy noise, and you can also have a drift. So drift is not really important. Gaussian white noise, it's really a restriction that we've chosen to make to keep things a bit simpler. And the other thing is you could also have negative jumps. But if you have negative jumps, somehow you will lose this polymer interpretation. So here this is not the true restriction. Okay, so this is the kind of Levy noise we will work with, those that are pure jumps and that have only positive jumps. Okay, so now let me go back to the stochastic heat equation and talk about a bit about the case with Gaussian white noise. So it has been known since the 80s that the solution of this equation in dimension 1 is well defined and well understood. And Hubert, Khanin and Quastel, to define the continuum polymer model, they built on this solution to basically construct the transitions probability for this continuum polymer measure. And the object they constructed, you can write it as follows. You can say that this continuum polymer measure in Gaussian white noise, it has a formal density with respect to Lebesgue measure, which is given by the exponential of the white noise, which is integrated along the graph of the trajectory of your Brownian motion. So this thing doesn't make sense for one given trajectory, but if you integrate it with respect to some the Wiener measure, it kind of makes sense. So this expression for the partition function makes sense. And if you want to integrate against some measurable event, you will be able to make sense of this. Okay, so you have a measure which is singular with respect to Wiener measure, but somehow formally it has a density of this form. And what Hubert, Khanin and Quastel also proved, not in the same paper, but in a paper that was published in the same year, is that this continuum model is indeed the scaling limit of the discrete one. That is that if you take beta n that tends to 0, like n to the minus 1/4, then the distribution of the rescaled trajectory converges to this random distribution, which is a continuum directed polymer. Okay, so this is about what was proved in the Gaussian case. There are a few open questions actually and research programs in higher dimension, and it's really a different game because in dimension larger than 2, this equation has no solution, at least in the classical form. And if you want to make sense of this, one way to do it is to convolute the noise with a smooth kernel and then rescale it when you take the mesh of your convolution to 0, rescale the intensity of the noise to get a non-trivial limit. There has been some progress in this direction in dimension 2 by the following authors, and also in dimension 3, but dimension 3 is very different from dimension 2 here. And in this case, it's believed that in dimension 2, the scaling limit of the directed polymer should be given by this scaling limit of the stochastic heat equation. Okay, so the solution of this ill-posed equation, but this is really something different because, okay, in dimension 1, the solution really exists in the classical sense, and this is also what we will deal with today when we talk about Lévy white noise. Okay, so let me talk now about the stochastic heat equation with Lévy noise. So, okay, so let's place ourselves in RD now, and let's look at this equation. And it has been proved by Saint-Loup-Berbier and then by Chong with more general assumption that this solution admits a solution provided that your intensity satisfies some assumption that we will, I will talk more about it later. This assumption that you have on lambda is something that you sometimes really need, and it depends on the dimension. Okay, and some other authors have worked on this in between. One issue with this work and our problem is that in both authors, they require some regularity for the initial condition, which is possibly problematic for the polymer measure because we want to work with Dirac mass initially. But to be fully honest, the reason why we didn't start with the solution of this equation when we wanted to build our model is that we didn't know about this work first. And this was when I gave first a talk that Carsten made me aware of this. And I think this helped to improve our work and to look for further things. So I'm quite grateful for this. So let me talk about the approach we took. And our first observation was that actually, if you want to look at the solution of this equation, even if you don't know much about SPDs, you can work this kind of intuitively when the noise intensity is integrable at 0. So when U is integrable at 0 for the intensity. So this is the case where actually you don't need to put a drift to compensate for the jumps because your measure doesn't explode locally when you don't put a drift. So, okay, in my definition, I've considered a drift to compensate the jumps between 0 and 1, so I will keep it. But the drift term is not a problem. You can suppress it just by multiplying your solution by some negative exponential. Okay, so let's say that now we have taken into account the drift, and we can just look at psi like just a process with just positive jump. And if you want to find the solution of this equation, well, just run the heat equation, and each time you run into an atom, just multiply the current value. Well, just add a Dirac mass to your solution, whose intensity will be, well, the intensity of the atom you encounter times the actual value of your solution. Okay, and if you iterate this, basically, you get a solution of the following form. So the formula is quite ugly, but it's not very complicated. Basically, you will sum over all possible collections of points in your process. Okay, and okay, you will want the all collections of points whose time coordinate is between 0 and t. Then for all these points, you will just multiply the intensity, and then you will multiply everything by the probability, well, by the probability density of visiting these k points for Brownian motion, and then visiting one extra point, which is the point at which you are evaluating the solution. Okay, so I don't know if I conveyed the message well, but this is quite intuitive that this should be the solution, okay? So I gave here the expression for rho, which is just, well, the heat kernel for going through these k points here and ending at xt. So, okay, so that's one observation. The other observation is that actually, when you look at this, you can even define directly a continuum polymer model that would correspond to this environment psi. Okay, so if you think as u as the endpoint density distribution of your polymer, somehow to have the full polymer measure, you just have to take into account what happens along the trajectories that go through these k points. So let me go a bit more through that. So if you recall, when I introduced the discrete polymer measure, if you want to compute the probability of an event, again, for this polymer measure, you have to compute the ratio of two things. So on the denominator, you will have the partition function. And on the numerator, you will have this product of 1 plus beta eta integrating it against the event A. So I will call this the partition function restricted to A. So for the continuum model, we will have something that has the same form. So we have to define the partition function that corresponds to each bounded measurable function. Okay. And in order to find the partition function, well, a reasonable definition for the partition function associated to a measurable function is, well, we'll do the same thing as before. We sum over all finite collections of points with coordinates, time coordinate between 0 and 1, I guess, because I'm looking at the continuum model with time horizon 1. And then I take the product of the intensities and I multiply by, okay, some heat kernel as well. So I still look at the probability of going through the all these k points. And then I have to average f along all Brownian trajectories that go through these points. So I will just multiply by the expectation of f of a Brownian motion that is conditioned to go through these points at these times. Okay, or to go the graph of a Brownian motion that goes through these space-time points. Okay, is the definition okay? And basically, this gives you, this is a linear combination of positive measures. So what you get in the end is a positive measure, and because you renormalize it, you have a probability on the set of continuous trajectories. Okay. So, okay, I have to take my charger because my computer will go off. So I will stop 1 minute.
Maybe let me ask the audience if they have any questions. If you have questions, you can either put it in the chat or just unmute yourself and ask the speaker. So I think Hubert just disconnected. So I hope that his laptop didn't die in those 5 minutes. So I hope that he will be back soon. Let's wait for a couple of minutes.
So I have a question, Karsten, maybe you can answer. But so he's been working with these series. They look basically like chaos series, right? So this is the same idea. It's just that they don't have any of the nice orthogonality that you would normally assume of a chaos series, right?
Exactly. So these are just expansions in terms of multiple integrals of the solution. Yeah, but they're not orthogonal because you don't have covariances or something like this. I think he's back.
But does it really matter that they're not? I guess when it's useful when you want to prove L2. When you want to prove convergence type bounds that it's orthogonal, right? But how much complicated? How much more complicated does it become when you don't have this orthogonality?
I think so. For multiple integrals, or multiple Levy integrals, it's not the orthogonality that's the most problematic, but it's rather that you don't have a good moment bounds. So you have some upper bounds, some lower bounds, but you don't have sharp ones. That's the main problem, I would say. Okay, very good. That looks good.
Okay, yes, I'm on mute. Okay, that's good. Okay, I'm very sorry for all this. I discovered that the router was not working just before the seminar. It got me. Okay, so where was I? Here. Okay, so now we have defined a reasonable notion of continuum model for noise whose jumps are locally summable, okay, where you don't have to compensate for this drift. So one thing you have to check once you introduce this definition, you have summed lots of things that are positive. You want to check that this sum is finite. And okay, the first thing we did with Quentin was to, okay, not the first thing, but one thing we did eventually with Quentin was to find a necessary and sufficient condition to have finiteness of your partition function. Okay, and this condition is quite mild. You just need that log of u to the d over 2 is integrable at infinity for lambda. And for the rest of the talk, we will consider that this holds, okay, and not talk about it anymore. Okay, so this is the only condition you need so that the partition function does not explode. Okay, so now let us talk about the most interesting case, which is the case where actually, well, u is not integrable at 0 under the measure lambda. So in that case, what you can do is, well, consider the continuum model associated with the truncated noise with threshold R, which I introduced earlier. Okay, and this gives you a continuum polymer. Okay, it's just that you have suppressed all the small jumps. Okay, so we take the same thing as before, but except that we consider only the points here for which the third coordinate is larger than A, and for the drift, we just subtract the part of the drift which corresponds to these jumps. And now the question is, if you consider this measure, send A to 0, do you have a limit when A goes to infinity? And of course, the best way to have a limit is for the numerator and the denominator to converge to something which is non-zero for positive f, and we will be fine.
Hubert,
So,
you mean probably A to 0, right? Not to infinity.
Yes, I mean A to 0. Yeah, thank you. So a key point there is that if you look at your partition function as a function of A and you look at it with the appropriate filtration, then it's a reversed local martingale, time reversed local martingale, and it's also CAD-lag. So as a consequence, when you consider F, which is non-negative, for free, you have convergence when A goes to 0. And the main issue is to check that the limit is positive. Okay, well, in particular, you want the limit to be positive for the denominator. So this is what we checked with Quentin. So in dimension 1, actually, apart from this condition for large jumps that I discussed before, you can define the continuum polymer with Levy noise for any kind of noise. The only condition you have is, well, the condition for the noise to be well defined, which is u squared to be integrable at 0. Okay, and somehow this result is not completely empty. If lambda is not the intensity which is corresponding to a noise because it's too heavy on 0, your limit is degenerate, so that somehow you can't define continuum models for things that would be more irregular than the noises, in a sense. Okay, this is something, well, somehow expected, but it's always good to check this, because making A tend to 0 here, you don't require lambda to satisfy this a priori. So, okay, when dimension gets larger, somehow you start to get more restrictive condition. And what we proved is that you get a non-degenerate limit when u to the q is integrable at 0 for some q smaller, strictly smaller than 2 over d. And it turns out that this condition is almost necessary, because if u to the 1 plus 2 over d is non-integrable at 0, then your limit is degenerate when d is larger than 3. And when d is larger than 2, you have actually more than that. So if u square log u is not integrable near 0, then your limit is degenerate, which means that in dimension 2, unlike dimension 1, there are noises for which you can't define the continuum model, or at least you can't define it as we did. Okay, and finally, I mean, I think this is the important point. In all cases where we have proved that the limit is non-degenerate, our truncated continuum polymer measure converges to a limit in the weak topology. Okay, so before going back to discrete polymer, maybe I want to say something about this this measure. So first observation is that this measure is singular with respect to Q as soon, well, in the cases where U is not integrable at 0. So when your jumps are not, when your noise has not bounded local total variation, you end up with a measure which is singular with respect to Wiener measures. So you have no density. But if you consider you measure average with respect to the environment, then you recover something which is absolutely continuous with respect to the Wiener measure. And this was something that was already observed in the case of the continuum polymer with Gaussian space-time white noise. Okay, and another thing which this time contrasts with the case of Gaussian space-time white noise, or well, is that when dimension is larger than 2, somehow if you take 2 replicas of your continuum polymer and then take average with respect to the environment, then you get something which is not absolutely continuous with respect to well, 2 replica of the Wiener measure. And the reason for this is that if you take 2 independent realization, two independent realization of trajectories with this measure, with positive probabilities, they will intersect. Okay, so, and this does not happen for two independent Brownian motions. Okay, so now let me go back to the discrete model. So, okay, let's remember that we have a model with a random walk, and you modify the probability of the random walk by multiplying the original probability by a product of 1 plus beta eta, where the etas are IID random variable with heavy tails. Okay, they are in the domain of attraction of an alpha stable law. And we want to have a scaling limit result for this model. So what we have proved is that if you rescale beta n like n to the minus this, so minus d over 2 alpha times 1 plus 2 over d minus alpha, and if alpha is smaller, I don't know why you have an F here. If alpha is smaller than this alpha c, which is 1 plus 2 over d, or well, the max of 1 plus 2 over d and 2, so that this thing is positive, then you have that the law of the rescale trajectory under the polymer measure, it converges in distribution to a limiting law, which is a continuum polymer with alpha stable environment. And basically you have a, well, if you have this prefactor in front of your n minor thing, you will find this prefactor in front of the noise there. And what we obtain is that, in fact, the noise you obtain is indeed the limit of the IID environment seen as a distribution. And well, there is a small subtlety here, which is the reason why you have factors 2 everywhere. It is that, in fact, you have to consider only the environment on even sides. Okay, you want n and x to have the same parity, because the other sides, they shouldn't care at all because the random walk can't visit them. Okay, and what we have is that, okay, if you take environment on these sides, rescale diffusively, and multiplied by the right factor to have things on the right scale, then you have joint convergence of the environment and of the measure to the white noise and the continuum polymer with the white noise. Okay, the alpha stable Levy noise. And this joint convergence, somehow, this is something that also holds in the Gaussian case, but it was not so much advertised or remarked. But somehow recently, there was a work by Soon and co-authors on the Ising model where they proved this also for a Gaussian model. Okay, so I don't know how much time I have left, so please stop me if I'm taking too long. Or
still have 50 minutes.
Oh, okay. So okay, so I will have time to say a bit about the proofs. So okay, when you want to show that your partition functions have a positive limit, you need to show two things. So the first thing, you want to show that the probability of being positive is either 0 and 1. So to prove some kind of 0-1 law, and there is something missing here. And I mean, this is not completely obvious, but if you think about it, this comes from the usual arguments. So there is not so much to say about it. Then the big part is to show that your martingale is uniformly integrable, so that it can't converge to 0 with probability. Well, its limit can't be 0 with probability 1. Okay, so I say the martingale, actually in some cases you can have a local martingale, but this is only because you have too many big jumps, and by some truncation argument you can reduce yourself to the case where you have a martingale. And to show uniform integrability, somehow it's a bit delicate because, okay, the only things that are easy to compute are integer moments for this thing, because fraction, well, if you take z to a power which is not an integer, you will have difficulty to compute anything. And the second moment is infinite. So what we decided to do is to make some surgery on the partition function, taking the parts that were making the second moment infinite, and to show that the rest had bounded second moment. And okay, this was probably the most technical part in the paper. So now let me just say something about the discrete model, and this is really well, one of the better way to justify our approach with truncation is that we use this truncation approach to prove the convergence result. So what we did was to consider a discrete model which mimicked this truncation thing. So we modified the environment by taking keeping the variables eta if they were bigger than a on the right scale, okay, on the rescaled scale, and replacing them by their conditional average if they were below this threshold. And basically, this has the effect of just keeping the few extremal points in the process, but when you get a to 0, they get more and more numerous, and eventually you get the full limit this way. So when you fix a, because you have only finitely many points in your environment, it's technical, but it's kind of intuitive how that to prove that this converges to the continuum model with truncated environment. And then what you have to do is take a to 0 on both sides of this convergence, so that you have to show that basically the partition function of the truncated model converges to the untruncated one uniformly in N. And this is the part which is really technical. Okay, so this is what I wanted to say. Thank you very much for your patience, and I apologize for, well, going away in the middle of the talk. Okay, I'm sorry.
No problem. Thank you very much for the nice talk. So are there questions from the audience? You can just unmute yourself and ask. So maybe I have a question. So in the beginning, you restricted beta to be between 0 and 1. So why is that? So is that necessary that you just have beta smaller than 1? Yeah, here.
Okay. Yes. No, it's just these two assumptions that are somehow coupled, so that this thing is always positive.
I see.
Okay, but I mean, if you want to
consider. Oh, I see. Otherwise, you would need to change the -1 probably.
Exactly, but okay, as you make beta tend to 0, I mean, actually, unless if the tail at infinity is much larger, well, is much heavier than the tail at -infinity, this wouldn't change much. It's just that you would have start with a signed measure, which is something not very natural. Okay. But yeah, even eta being having a bounded support on one side is not truly necessary in a sense.
Okay.
So I have a few questions. What can you say about Holder continuity or different continuity properties of this limiting equation? You know, does it have kind of fairly obvious properties? Or?
I can't remember exactly in which space it lives, but it's really discontinuous because basically, okay, if you fix the time marginal, it will be finite almost surely and maybe continuous. I'm not sure, But at points where you have atoms, you're adding this Dirac mass. So basically, this will force your equation to be highly discontinuous. Because I mean, there are times at which your time marginal is not a function; it's a distribution because it has these Dirac parts.
And what about the long time behavior of this? Is there any understanding of what that might look like? You know, I'm just thinking something like, you know, the usual KPZ sort of story, but
yeah, so I think it should be at least as super diffusive as KPZ, but it's
well, because there's this, you know, work of people in last passage percolation dealing with heavy-tailed environments.
Yes. Okay. So this is a bit different. So this is good to talk about it because here our environment. I mean, they are much more like gamma laws, if you want. They are really variants of well, they are the tails. If you look at the tail, okay. If you look at the tails, if you make this change of variables, okay, if eta was in the exponential, this would correspond to exponential tail. Okay, because exponential beta eta has a tail like minus, well, as a tail, well, this is the quantity that is in the domain of attraction of an alpha stable law. And the reason why we took this formalism is we didn't want alpha to depend on beta because beta has to tend to 0, so our thing wouldn't make sense. So this is much less heavy tail than these last passage percolation things you're talking about. And for this reason, yes, for me, it's not clear whether on the long term you shouldn't care that much about these heavy atoms and you should still remain on KPZ, or maybe you should see these things a little bit, but I don't see how it could be strong enough to change the exponent. But yeah, but then I mean, there are absolutely no results. So
also, so there was some work kind of following up to Albert's Khanin and Quastel of Partha Day and Nikos Sigoros, where they show as long as I think there's 6 moments, you know, you have the same stochastic heat equation. So just to kind of put what you're doing in that context, so are you kind of looking in that same frame, but between alpha 1 and 2? And then,
so this yeah, I don't, yeah, so this 6 moments here, it's really, okay, in the paper of Albert Khanin and Quastel, actually, at some point, they just look at this because it's more convenient. And then they look at this and make the truncation.
Mm-hmm.
And when they prove the result with this, second moment is all they need.
Right. Okay.
The 6 moment thing comes from the fact that, well, you want to make sure that the maximum of this will not have some nasty effect. Okay, and this is where the 6 moments is required. And somehow it okay, this part really depends on the nearest neighbor assumption on the walk, I guess. If you would have walks with I mean, still with finite second moments, but that are allowed to jump far away, even I think higher moments, well, 6 moments could possibly not be enough. So I think this 6 moment is really some, well, okay, to make sure that the heavy things don't mess up too much. But if you look at this from this perspective, really, there is nothing between 2 and 6. Okay, things start to be Gaussian starting with the second moment.
Okay.
May I add one comment to the long-term behavior of this equation? So what is known is, for example, that even if you don't look at, you know, heavy-tailed noise, but just, you know, standard Poisson noise, so jumps are all of size 1. When you look at, you know, the long-term, say, Lyapunov exponents of the moment Lyapunov exponents of the equation, then you will first find that they grow much faster than in the Gaussian case. So you still have exponential growth, but the coefficients themselves grow not in a cubic fashion, but rather in an exponential fashion. So that's why, you know, people expect that the peaks, the intermittency peaks that you will see in, you know, those heavy-tailed equations will be even much larger. So yeah, but it's not that something that has been formally proved so far in the heavy-tailed case. Yeah. Okay. Are there further questions, comments, remarks? Okay. So if not, let's thank Hubert again for this very nice talk. And we will come back at 3:35, so in 7 minutes for the next talk. Clément, are you here? So if you're here, you can start sharing your screen so that we can.
All right, let me do that. I think Hubert is still sharing.
So you cannot just share without.
Well, it writes you cannot start screen sharing while the other participant is sharing.
Can you try now? I think I now.
Okay, now it works.
Change the setting. Yeah. Okay.
All right. Okay. All right. Does it work?
Oh, I still see Hubert's screen. So why is that? Let's see. Hubert, can you please unshare your screen so that Clément can share?
Yes.
Okay, now it's there.
Okay, all right.
Very good. I'll be back in a minute, okay? Clément, are you ready?
Yes.
Okay, so welcome everybody back. So our second speaker today is Clément Cosco from the Weizmann Institute. So Clément did his PhD in 2019 at Paris 7, and then started the postdoc position at Weizmann Institute afterwards. So we're very happy that you're here and look forward to your talk titled The Carter-Parisi-Chang Equation and the stochastic heat equations in dimensions d greater or equal to 3.
Okay. Hello, everyone. Thank you very much for the invitation. And I'm really happy to be here and to talk. All right. So as Carson said, I'm going to speak about these two equations. And so let me get into the subject. And first say what are these equations? Formally, they are given by diffusion SPD, where you have Laplacian term and plus a noise, which is multiplied by the solution U. So we call also this stochastic heat equation with multiplicative white noise. And Hubert has talked a lot about it in the previous talk. And I'm considering the equation on RD, and Xi here is a white noise on space-time white noise. So this equation is associated via the Hopf transform to the KPZ equation. And the Hopf transform is just simply taking the log of U. And then you will end up with a SPDE, which has an extra term, which is a square of the nabla of H, and plus noise. But this noise is not multiplied this time by the solution. There is, okay, it's not easy to make sense of this equation, except maybe in dimension 1 for the stochastic heat equation, because one of the problem is that you may be ending up with multiplying two distributions. For example, if U is only defined as a distribution and Xi is only defined as a distribution, you may have to multiply the two, or here you may have to multiply to take a square of a distribution. And only in dimension 1 for the SHE, you have that U is a defined pointwise and continuous, and it's easier to do it. But already in dimension 1, it's not that easy to make sense of the KPZ equation directly without using the Hopf transform. So how do you go from this formal definition to something you can trace? Is by modifying the noise. So here I'm looking at a modification of the noise which are only in space. So you take a smooth function phi, you construct this phi epsilon, which is approximation of a Dirac, and then you will have that this modification in space of psi epsilon converges to the initial white noise. But this is smooth enough in order to be able to define the regularized version of the SHE. So now if you take noise, the regularized noise, then actually this equation is well defined. And we will take in higher dimension, where I will focus the talk, you will take also another term which you will multiply the noise by is this epsilon d minus 2 over 2 factor. I will come back on that a bit later. And you can also construct the regularized version of the KPZ just by taking the log of U epsilon. So what we are concerned about the limit as epsilon goes to 0 of these two objects. And let me just mention that in dimension 1, there is not this epsilon minus d minus 2 over 2 factor. So here you see the noise is not multiplied by this. And if you take the solution and take the limit to 0, you end up with a non-trivial object, which is the definition of the solution of the KPZ equation. So this comes back to works of Bertinic and Creny, where they did it for the going via the Hopf transfer for the stochastic equation, but you can do it directly for H epsilon, and there are many works or higher and others that have been doing that. And let me just also say that all of this is related to taking the limits of the polymers, as Hubert explained just before. If you take the scanning limits of polymers, you actually end up with the SHE or the KPZ equations. And this comes from works of Hubert, Khanin and Quastel. Also consider it when you take a noise, which is a Poisson noise, and take a scanning limits. And you can also do it, as Lacoin explained, with heavy-tailed noise. So let me go back a bit, conservation with directed polymers, although Hubert did a lot on that. So here I'm working in a continuous framework, and I'm looking at a polymer with an energy that is defined as such. So you take a pass B. Pass here is RD, and here is time. And along this path, you look at the noise around it. Well, you do a small average by this test function phi, which is the same as the phi we were looking at before. And you can define this energy of the path inside the space-time white noise. And then you can define the polymer measure, which is a measure on the path space, and which is proportional to E beta, the energy, and the probability under the Wiener measure of the same path B. And so very similar to what Hubert just explained, but here I'm looking at the exponential way, not the product as before. And if you want this probability measure to be defined this measure to be a probability, you can just divide by ZT, which is taking the average over all paths B of this exponential term. So how does the connection goes with polymers is that if you look now in diffusive, if you take the white noise and you take a rescale version diffusively, and you can also reverse the time in this rescaling, then if you multiply it by a good rate like this, you will find that this rescale white noise has the original law of the white noise. So coming back to the equation, if you apply the Feynman-Cat formula to the SHE equation, you will simply find that this equality holds, that if you start with a flat initial condition of the SHE, then the solution of the SHE is given by the rescale polymer function, so you rescale it in time and in space, for this under this rescaled noise instead of the original noise, and at the temperature beta. So let me mention that this is an important fact of taking this epsilon d-2 here, is because if you take exactly this temperature, you will find here beta. Now, if you were in dimension 1, for example, because this formula is valid in any dimension, instead of beta here, you will get beta times the epsilon term, where and this term would go to 0, and it would be similar to what Hubert was talking about just before. But in higher dimension, in dimension bigger than 3, you want to keep this beta of order 1 inside the polymer. You don't want to take a limit as beta goes to 0 at the same time. Now, because this xi epsilon has the same law as the original xi, actually your epsilon has the same law as the rescale partition function. And you can also have similar expression using the Feynman-Cat formula for general initial condition. And in discrete, Hubert just proved actually this formula by simple calculus. Okay, so what is the interest of having this polymer point of view? in having this polymer point of view is that this ZT this partition function is a martingale, and in dimension bigger than 3, it satisfies a phase transition in beta, in the sense that when you are below this beta c, below a parameter beta c, then ZT will converge to a positive limit. Whereas if you are above beta c, so here, ZT will converge almost surely to 0. And you also have a subregion of weak disorder where you can ask for ZT to be bounded in L2. In particular, this will imply that the limits of ZT is positive, so you are in weak disorder. So this is a subregion of the weak disorder. And this region has been quite important for polymers in high dimension because it's a region where you can do a lot of computations because you have second moments. So you can check a lot of things. But we'll see that it actually plays an important role also for the behavior of the polymer. These regions have importance in terms of polymers because in the whole weak disorder region, you can show that you have under the polymer measure, the path stays diffusive. Whereas when you are in the strong disorder region, so when beta is very big, you have the noise plays a more important role, and your path will actually localize in very small parts of the white noise because it will be really attracted to where the white noise takes big values. And this has been really studied a lot in discrete case, and most of the results apply to without much change to the continuous case. And it has been shown, for example, in discrete that beta C is strictly less than beta 2 is strictly less than beta C. And we believe that the same kind of techniques will show the same for our model, which is now in continuous time and space. So what does this imply on the polymer, on the SHE and KPZ equation itself? So what has been first shown by Mukherjee, Shamir, and Zaitouni is that, so recall that we have just seen that U epsilon has the same distribution as the polymer partition function at time epsilon minus 2t. And so in particular, if you are above beta c, you will get that U epsilon will go to 0 because the partition function goes to 0 in this case. And if you are below beta c, then in distribution, U epsilon will converge to the infinite volume partition function. So this is where when U0 is 1. And so this is a pointwise point of view, right? You fix T and X, and you look at the limit. And you can ask what happens when you look at U epsilon as a distribution, because in high dimension, this is maybe the right way to look at them, is you can show that if you are below this beta C threshold and you start with any continuous profile, then when you test your function against a tense function f, you will converge to okay, your solution in terms of distribution will converge to the solution of the U bar of the deterministic heat equation. So it's only okay. It's a deterministic term, and in fact, you can think about this as a law of large number, because what will happen is that the U epsilon field will become the correlation between 2 points x and y will go to 0 as epsilon goes to 0. So basically, you will sum independent variables, and you end up with a limit which is the average, and okay, so this is a bit the reason why you have this deterministic object in the end. And it's quite different from dimension 1, where U epsilon converges to some very random object, a random solution of a non-trivial equation. So, all of this was, the second point was only proven for by Shamov, Zaitouni, and Mukherjee for beta less than 3t less than beta L2. And with Shuta Nakajima and Makoto Nakashima, we extended the result to the whole beta C region. And this used some techniques from Kometz and Yoshida about the central limit theorems for polymers. And homogenization techniques that we added to the recipe. So we also wanted to understand what happens when you start. So this was for a continuous profile. Okay, if continuous profile, and we wanted to understand what happens if you have a Dirac initial condition, as here. And we proved that in the whole weak disorder region, what happens is that you have actually a purely random term that comes and factorizes the solution. And it comes from the fact that when you start with the Dirac initial condition, the dependence of U epsilon on the noise around the starting point will be really important. It's a feature of the polymer that if you look locally, if you have a partition function condition to end at some point, it will depend non-trivially on the noise around it. So the Dirac mass adds a dependence on the noise that you cannot avoid. So the covariance here will take this into account, and this infinity appears at the limit. So let me continue about now pointwise properties. We've seen that when you start from a flat profile, you have these two convergences, but okay, we'll focus now all the time on weak disorder where things are non-trivial, because above it it's always 0. And we want to understand more about this convergence. Here it's only in distribution. You want to say a bit what happens in probability, or in a stronger sense. And what we have shown with Francis Kometz and Chiranjeev Mukherjee is that if you start from a continuous initial profile, so SHA, the KPZ equation, and in the whole L2 region, then the solution of the regularized KPZ can be well approximated by the sum of two objects. One is a stationary solution of the regularized KPZ equation. It's stationary both in epsilon and t, and also in x. And you have another term, which is a deterministic term, which is simply the log of the standard heat equation. And this depends on the initial profile. So the initial profile of the heat equation will depend on your initial value of H. So, so this is a bit, and this is now a convergence in probability. So this is a more subtle description of what happens at the pointwise level. And you have a similar statement if you start with Dirac initial condition, but you will have another copy to add of the stationary field because, again, of the dependence on the starting point. And we also showed in this paper that the H epsilon and the stationary solution have all positive and negative moments in the L2 region. So let me just say that this was also independently observed by Dunlap, Rezik, and Zaitouni, but at the level of the SHE solution. Okay, so let me talk about now. We've seen first order approximation when the epsilon goes to 0, and I want to go a bit now about the fluctuations you can obtain. So let me say again that in the whole weak disorder region, you have this law of large number when you integrate over the density function the solution, u epsilon. And what has been first shown by Gurezek and Zaitouni is that if you look at the difference between this term and this term, so here is the difference tested against the test function. And if you rescale by a correct factor, you will end up with a U1, which is a solution of the Edward-Wilkinson equation, which is described here. So the Edward-Wilkinson equation is a stochastic Heat equation where the noise is additive. And it's not, the psi here is not multiplied by the solution itself. You don't consider this, which would be the SHE with multiplicative white noise, but you multiply it by something which is deterministic here. It's a deterministic object. So U1 is actually a well understood object. It's a Gaussian. It has Gaussian law, and it has quite trivial rescaling. And in particular, it's much different from what happens in dimension 1, where the stochastic equation with multiplicative noise happens when you appears when you take the limit of u epsilon. Here in this all beta 2 region, L2 region, what you see is not KPZ type of universality class. So for those who know more about this. And let me also say that when you take the limit as beta goes to beta L2 of this object, it blows up. So in particular, it is expected that the result is optimal in the sense that it's optimal in the whole L2 region, and some different kind of behavior should happen after the beta L2 point. Now, so what we did with Shuta and Makoto was to extend, so the results of Gurezek Zaitouni was for beta much smaller than beta L2, and we extended it to the whole beta 2 region. And we also extended it to join convergence in time and space, which was not done before. Now we also proved it at the level of the KPZ equation. It's not trivial to go from one to the others because you're testing against a test function. So going from here it's the log of u epsilon, and going from the log of u epsilon from u epsilon to the log is not easy inside the integral against the tensor function. So it's not trivial to go to one or the other, and actually it's much harder to prove it at the level of the KPZ. And this was first observed by physicists Magnan and Unterberger, and then proved maybe in a more common way by Dunlap, Gurezek, and Zaitouni. So they proved it, both of them in a restricted part of the L2 region. And with Shuta and Makoto, we extended it to the full L2 region, and also to any initial profile, continuous profile, which was not done by the previous work, and also to joint convergence. And again, if you look at the fluctuations, you end up with an equation which is of the Edward-Wilkinson family. So you can do the same actually. So we prove that you obtain similar things when you start from the stationary solution, and then you end up with the Edward-Wilkinson here with a stationary solution of the Edward-Wilkinson that actually has Gaussian free field marginals, and this result actually writes in a different way when you look at the polymer itself, because the stationary solution has actually the law of log of the infinity. So what you actually find is that in the whole L2 region, the fluctuation of the log of the partition function converges to the Gaussian free field. So at the level of the polymer, it really explains if you take a diffusive limit of the polymer, then the field of the partition function looks like a Gaussian free field in dimension d bigger than 3. You can have the same as the level, not taking the log and subtracting by 1. Let me just finish now by talking about the diffusion the fluctuations at the point-wise level, because we've talked about when you integrate over a test function, and now I want to say more about when you don't average over a test function, but you look. So what you look at the pointwise property. So what we've said is that when you have an initial continuous profile, then you obtain this pointwise behavior. And if you take a flat initial profile, you can show that this is 0. And what we've shown is that the fluctuations. So if you take this object here now, which is here, and you look at the correct rescaling level, then you will find that this converges to a Gaussian process H, which follows the deterministic heat equation, but it started with a random Gaussian free field initial condition. And so this holds really at the pointwise level. You don't need to integrate, but it also works if you integrate over test function here. But the rest, the result is much different from the one before, because the one before you actually replace this by expectation of H epsilon. So these are two different centering. One is random and is also true at the pointwise level, and the other one is deterministic and not true at the pointwise level. And okay, so this is a bit what I wanted to tell you. Let me close by mentioning some remarks. All here we've translated the problem of SHE KPZ to a continuous polymer, and if you start all this from a discrete polymer and you do the rescale limit of the polymer, the diffusive rescale limit of the polymer, you will, this has been done by Dimitris Likonis and Nikos Zigoras, and they also proved it at the same time as us in the whole L2 region, using quite different techniques. And okay, so let me now just say a few questions that we still have, is that we don't know what are the nature of the fluctuations at the pointwise or average level above beta 2. So as I mentioned, we don't expect that they are the same. They should, because there is a parameter that explodes at beta 2. So it's quite interesting to wonder what happens. And also, again, in the beta 2 region, the techniques we used don't seem to be enough, or maybe the phenomena is a bit different, but we cannot understand exactly what happens when you start with Dirac initial condition, or not in an entirely satisfactory way for now. Okay, so thank you for listening, and I'd be happy to answer, or to try to answer to questions if you have some.
Thank you very much for the very interesting talk. So are there questions from the audience?
Yeah, I have a question, if that's okay. So you talked about this region between beta L2 and beta critical, and sort of the behavior there on the last slide.
Yes.
Do you expect those fluctuations to be Gaussian at all? Or is there any evidence for it to be Gaussian or not Gaussian?
At first we thought that probably there would be still Gaussian at the beta 2 point, also with different rescaling, because this is what happens, for example, if you look at the Biggins martingale of branching the branching random walk, you can have similar questions for the partition function, and this has been shown that exactly at the L2 point, if you change the rescaling, then you will find something Gaussian. But I didn't, I have not tried to do it, and I think that I've talked with people that are interested in that, and they say that maybe the behavior should be different than that. So, and maybe more similar to what happened in dimension 2 of the polymer, where around the L2 critical point, you have very specific and different behavior, which are not Gaussian, not alpha stable or something. So I'm not sure.
Thank you.
Further questions?
I have a question about, I think it's slide, I don't know, 16 or 15. When you say that the H converges to the free field.
Yes. This is it, or
no,
or
that's
before?
the one. No, after there is.
Okay, this one.
Yes, I think this is the one.
Okay.
So you say that it's all when integrated, but also pointwise. But I thought that the free field itself was not defined pointwise, so I'm a bit puzzled here.
Okay, it's for T strictly positive, and actually for T strictly positive, you are looking at the solution after some time evolution of the heat equation.
Ah, so the free field, okay, the free field is the initial, okay, yes, you have no noise in that equation, so it becomes regularized. Okay, so I understand. And I had another question. You prove law of large number below beta C.
Yes.
And above beta C, you prove that you converge to 0 pointwise. Can you also prove that you converge to 0 when you integrate?
Yes.
Okay.
At least if you are strictly above beta C. I don't know exactly at beta C or these subtleties.
Okay.
Okay, we have time for a last question, if there's something. Maybe I have a last question. So what type of techniques do you use to prove the CLT? So is it...
So we use Martingale's CLT. So we need only to prove that the bracket converges to some limit. Actually, so there are now different proofs of this, and there are 3 different proofs. One is going through this chaos expansion, and was done by in the discrete case by Dimitris Likonis and Nikos Zikouras, and the other proofs were done by Gouris Exaitoni and others, and they used more Maliavin calculus.
Okay.
And the third technique that was used is from the physicists, and it was more about renormalization techniques. And okay, I'm not really okay, cannot explain this at least.
Okay, thank you. So let's thank both speakers again. And then we will meet for the SPD seminars in 2 weeks again. Okay, so have a nice day. Bye-bye.
Thank you.
Thank you.
Thank you.